So today we'll start a series of 6 lectures on human memory. Some of this material, in particular this lecture, will be more or less review of things that we've covered in intro psych. So hopefully everybody sort of has some sense of, when I talk about sensory memory, when I talk about short-term memory, what those things are. But these two processes are quite important, and so we'll go into them in some detail in this lecture and look at their capacity, how much they hold, and for how long they hold information. Now, of course, why is memory important, right? Why do we care about memory? Well, memory allows us to retain learning, right? And so we can adapt our behavior and become better suited to live in our world. And arguably, all of the technology that we have, everything that we have that makes us human, is because of memory, right? We can remember what we've learned and pass this on to future generations. So the takeaway message, the big picture from all of these lectures is that we tend to think of memory as being something that's very static, very fixed, but in fact memory is actually very dynamic. And so hopefully by the end of these 6 lectures, you'll agree with me that memories are not exact replications of things that happened in the past. So this lecture on sensory memory and short-term memory is based on chapter 5 in your textbook. Now, memory was first modeled using the information processing approach by Atkinson and Shiffrin in 1968, and they constructed what's called the modal model of memory. And it simply proposed 3 stores, right? So we have a sensory memory store, and one of these memory stores presumably exists for every single sensory system, so vision, audition, touch, smell, taste, and so on. A short-term memory store, and short-term memory holds everything that we're aware of at any one moment, and a long-term memory store. And so this is information that we're not aware of, but we have stored in our brains, and we can recall this information, bring it back into short-term memory to become aware of it again. And so in Atkinson and Shiffrin's original model of memory, they proposed that control processes move information between these memory stores. And so we've already learned about one of these control processes, right? We just had 3 lectures on attention. And so attention under this framework is considered a control process that moves sensory information into short-term memory. And as we learned, if you don't pay attention to things in your world, it becomes less likely that this movement of information from sensory memory into short-term memory actually happens. So you have to attend to your world in order to be aware of it. Another, control process would be something like rehearsal, right? So studying for a test, the idea there is that you're trying to encode short-term memories into long-term storage so that during the test you can recall them and hopefully do well on the test. So again, I've said this before in prior lectures, what's the point of making models like this? Well, models allow us to make very, very clear predictions. So this model is positing that, we have 3 different memory stores. Do we actually see evidence for that? Do we see patients, for instance, that have lost their long-term memory or have lost the ability to make new long-term memories, right? So do we actually see a distinction between these 2 memory stores? And that's why, coming up with models in psychology is an important way to sort of generate hypotheses that we can then test in the lab. So let's just work through this model in some more detail. So imagine, for instance, that you have to remember a phone number. The situation rarely occurs today, but of course, before the days of smartphones, like when I was in university, you would have to remember phone numbers all the time. And so, you look something up on your computer, let's say, the phone number for your local takeaway Thai restaurant, and you encode that information in your sensory memory. So the visual image is represented in the firing of photoreceptors and other cells in your retina. You've attended to the image, and you're moving that information into short-term memory. So you become aware of it, right? Those numbers, in this case 555, 5100, are bouncing around in your brain. So anything that you're aware of, we can say that information is in short-term memory, right? So right now, the fact that you're aware of, hopefully, the sound of my voice, right, or what you're viewing on your computer screen, that information is maintained in short-term memory. Now, maybe this is, some sort of takeaway place that you plan to order from again. They have amazing curry, amazing pad thai. You're going to order from this place over and over and over again. And for whatever reason, you have some sort of old school phone, and so you can't just, record the number in your phone. So you have to remember it. And so what do? You rehearse the number over and over and over again, hoping to move it from short-term memory into long-term storage. And so when that memory becomes encoded, when it moves into long-term storage, what does that mean? Well, it means that the memory, in this case, this phone number, is actually represented by neurons in your brain. So new neural connections have been formed that hold that memory. But importantly, you're not aware of it, right? You're not thinking about this memory constantly. But when you decide that you're hungry and want to order from this restaurant again, you can draw that memory out of long-term storage back into your short-term memory store. You become aware of that information again. And so this is, sort of fundamentally how information moves through Atkinson and Shiffrin's modal model of memory. And of course, if you remember from intro psych, right, this model is necessarily incomplete. We'll talk a little bit about why it's incomplete in the lectures that are coming up. But this was a pretty good start, right? In that it nicely describes or nicely captures human behavior and makes some very clear predictions, right? It suggests, for instance, that we have these different memory stores in our brains, and so we should be able to observe patients that have deficits in one of these stores. So let's focus on the first box on sensory memory. What is sensory memory? So sensory memory exists for all of our sensory systems, and we can simply define it as the brief retention of the effects of sensory stimulation. Okay, so if you close your eyes for a brief second, about half a second, the image that you were looking at should persist. When I finish speaking, again, for about 1 to 2 seconds, the sound of my voice should actually sort of bounce around in your brain. Sensory memory also exists for other sensory systems, such as, touch. Touch the palm of your hand, pull your finger away, right? And you'll have this brief sensation that you're still touching the palm of your hand. And we can see sensory memory at play in a phenomenon known as persistence of vision. So in persistence of vision, there's some continued perception of a visual stimulus after it is no longer present. Right? So if you've ever played with a sparkler as a kid, right, on Canada Day, light your sparkler, wave it around, woohoo, country, you'll see this light trail. That is persistence of vision. That's a sensory memory. There's actually no no light there. It's this memory that's existing in your sensory systems. So sensory memories are the product, right, of residual neural firing in your sensory systems. So that information hasn't, I believe, reached the cortex yet. So sensory memory was first studied in the 1960s by George Sperling. Picture of Sperling in the top right-hand corner of your screen. I aim to look that cool wearing a turtleneck. And what Sperling was interested in was the capacity of our sensory memory store. Right, so how much information does sensory memory hold? And he designed this experiment. You may remember this experiment from intro psych. The idea here is that you view an array of letters and you have to report as many letters as you can from that array. And so when he initially ran this study, right, he simply showed people this array of letters very, very quickly, and they had to report as soon as the array disappeared how many letters they saw. And on average, out of 12 letters, they were able to report about 4.5. And most of the letters they reported tended to be on the same line. And that turns out to be sort of a very important aspect of his initial sort of finding. So let's do a demo of how Sperling's experiment would have worked. So I'm going to have you stare at this fixation cross. In a second, you'll see an array of letters. And after the array disappears, you basically want to write down or report as many of the letters as you can remember. And so that's a very challenging task. And what Sperling found, right, was that people were able to report about 4 letters. They tended to be all on the same line. But a lot of people said, I saw all of the array. I saw all 12 letters. That image was in my brain, but they just disappeared. That image disappeared too quickly for me to be able to report all 12 letters. And so I was only able to report one line. And so this made Sperling sort of rethink his study. And he thought, well, maybe sensory memory actually is, in the case of vision, is actually holding that entire array. And the problem is that it just, sensory memories fade too quickly. So participants only have enough time to report 3 or 4 letters. And so he redesigned his study so that participants were cued to report a particular row. And this cue was simply a high tone, a mid-range tone, and a low tone. And what he found was that when participants were given this cue, they were able to report about 3.3 letters, but they could report 3.3 letters from any line. So from any of the 3 lines. And so, yes, they're reporting fewer letters, but the fact that they can report letters from any row suggests that all the rows are actually in their sensory memory store. So they're holding everything that they're looking at. So let's do this new, what Sperling called a partial report task. So the way this works is that that tone means report the top row. That tone means report the middle row. And that tone means report the bottom row. And, I don't expect you to remember that. If you were a participant in Sperling's study, you'd have a lot of training. So you would associate each of those tones with a particular row. But the idea is that you're staring at a fixation cross. The array will be flashed at you, and then you'll hear a tone, which will cue you to report a particular row. And so in that case, you should have been cued to report KWBX. We can do that again. Do you recall the tones? So row 1, row 2, row 3, here we go. And so there you should have been cued to report AKVP. And so if we look at Sperling's data, with that whole report task, he found that participants were able to report about four letters from the array, so about 33% of the array. If you look at the partial report task and you simply ask, if you're cued to report row 1, how much of that row can you recall? The answer is a lot. If the tone immediately follows the presentation of the array, and you're cued to report row 1 or row 2 or row 3, you're pretty good at reporting the entire row. Now, performance drops off as a delay is introduced between the presentation of the array and the tone, but the takeaway here, right, is that this partial report task really does provide evidence that for a very brief amount of time, about half a second, that entire array is floating around in your visual sensory memory. And if you're cued to attend to a particular row, you can report almost that entire row. And so the limit here isn't the capacity of sensory memory, it's how long information lasts in sensory memory. And I think a lot of students struggle with this point, so I'll just repeat it. The limit here isn't the capacity of sensory memory, right? For all we know, our visual systems are holding, everything that's in our visual field at any one time. It's just all of that information is held for a very brief period of time. And if we actually want to remember and be aware of any of that information, we have to attend to it. So sensory memory, seems to be almost limitless in its capacity, but that information fades away very, very rapidly. So let's move on to talk about short-term memory. What we know about short-term memory is that this reflects what we are aware of at any one time. Short-term memory is our window on the present. And so efforts have been made to measure the capacity of short-term memory, both in terms of, how many things can short-term memory hold, and how long can you hold that information without rehearsing it. So what we know about short-term memory is that it's time and space limited. And we know this because of early work done by George Miller, who had participants memorize random digits. And so these digits varied in length. And what Miller found was that on average, people could remember about 7 digits. Right? So if you're shown a digit 3, 9, 6, 7, 8, and asked to remember it, that's a pretty easy task. If you're shown 4, 8, 2, 3, 9, 2, 8, 0, 7, and asked to remember it, it's a more difficult task. And so Miller coined this term, the magical number 7, plus or minus 2. And in his view, that was the capacity of short-term memory. And the thinking was that we could hold things in short-term memory, about 7 things, for about 15 to 20 seconds. So in practical terms, what does that mean? It means that if somebody tells you their phone number, you can have that number in your short-term memory and without rehearsing it, sort of come back to it at any time and be aware of it. Obviously, rehearsal allows you right? To extend the period of time that you keep something in short-term memory. If you repeat a phone number over and over and over again, you could theoretically, maintain that information in short-term memory forever, right? But eventually you're going to get distracted. You'll think about something else, and then the question is, how long do you have to come back to that original memory? About 20 seconds, it seems. So Miller's suggestion was that short-term memory holds about seven things. More recent estimates of the capacity of short-term memory, and I say recent, this was 1997, which was before probably most people in the class were born, so like 23 years ago, but cool study. So they used change detection. And so the way this works is that you see an array of objects for a very brief period of time, 100 milliseconds. And then you see a blank screen for about a second, right? So long enough that the sensory memory of the original array has disappeared. So any memory you have of that original array must necessarily now be in your short-term memory store, right? Because the sensory memory is gone. We've waited a second. And then you see another array of objects, and it's on the screen for 2 seconds, and you're asked, is this the same or different? Right? So in this case, you would say, oh, it's different. There used to be a black square here, and now there's a green square there. And so this allows us to test to see, how many objects can you hold in short-term memory, because we can vary the number of objects in the array. So down here, we have 8 shapes, 8 squares of different colors, much more challenging task. Same idea, they're presented for a very brief period of time, 100 milliseconds. We wait almost a second to make sure that sensory memory is gone and that any residual memory of these objects is maintained in your short-term memory store, and then you're shown a new array of objects and you're asked, is it the same or different? So let's do an example. This task is very challenging. 100 milliseconds is a very short period of time. So in this first one, I'm giving you 4 times the amount of time that you would have had in the original study, so 400 milliseconds. So you'll see, in this case, 6 objects, and then there'll be a delay of about a second, and then you'll see 6 more objects, and you simply have to say, what has been changed, if anything. Maybe nothing's been changed. So here we go. Prepare yourself. Okay, was something changed there? Yes. So you may have noticed that the red square used to be purple. Actually, the red and the purple squares were swapped. Okay, let's do that again. But this time, instead of 400 milliseconds, I'm going to give you 100 milliseconds. This is full speed. This would have been the speed at which the original study was run. Here we go. Prepare yourself. Okay, same or different? Different, so that orange square used to be green. So that's how the experiment worked. And what did Luck and Vogel find? Participants can retain about 4 objects in their short-term memory, right? So 4 squares, and the task is fairly easy, so you're able to see changes with about 85% accuracy. Once we get up to 8 squares, we're down below 75% accuracy. So accuracy is starting to fall off. So their conclusion was that, we can be fairly confident that we can hold about 4 things, 4 visual objects, in short-term memory. So there's a bit of a revision here, right down from 7. And as it turns out, we'll get to this in a second, as it turns out, it depends on how complex the things are that we're holding in short-term memory. So the more complex the things are, the harder it is to store them. And arguably shapes are more complex than numbers. So maybe that's why we've gone from 7 to 4. But before I get to that study, I should just say that, how we define an item is variable. So we can use something called chunking, right, to expand our short-term memory. And so this just involves organizing smaller units of information into larger, more meaningful units, right? So if I showed you these two arrays of letters and said memorize them, hold them in short-term memory, you'd have a very, very hard time doing that. But if you give, the letters some context, if you organize them in a way that is more meaningful to you, right, we can organize that bottom row into acronyms that represent television stations that we're all familiar with. Much easier to remember the letters. And I'm sure we could all remember CBC, HBO, CTV, TSN, and CNN if we had to, right? Those letters on their own, scrambled up, much more difficult to remember. And so this is an example of chunking. And so you can use chunking to actually increase your short-term memory capacity well beyond 4 or 5 things. So final question to consider as we come to the end of the lecture is this. Maybe short-term memory isn't limited to a number of items, maybe it's capacity limited, right? So think about a computer hard drive. You only have a certain amount of capacity on that hard drive, and what that means is that the amount that the hard drive can store depends on how complex or how big the files are that are on the hard drive, right? You could store, 10,000 Word documents on a standard hard drive, but maybe only 100 full-length films, right? Because they're much more complex, they take up much more space. And so more recent suggestions have been that short-term memory isn't limited to a set number of items, it's actually capacity limited. And so it depends on how complex the items are. And the more complex the things are that we're trying to store in short-term memory, the fewer things we can actually store in short-term memory, right? So as Luck and Vogel showed in their paper, if we're talking about colored squares, we can store about 4 squares in short-term memory. But as we make the objects more complicated, so as we move to Chinese characters, random polygons, and then shaded cubes, right, our capacity to store these items decreases. And so, if I asked you to remember the orientation of a bunch of cubes, you'd have a hard time doing that if there was actually more than 2 cubes. And so this is, some evidence that actually thinking about short-term memory as being item limited doesn't make much sense because items can vary in how complex they are. It makes more sense to think about short-term memory as being capacity limited. And so this idea was proposed by Alvarez and Kavanaugh in 2004. And again, if you just look at this figure here, and I believe they used change detection in the study, just like Luck and Vogel. But instead of using just colored squares, they used more complex items, and they found that your ability to detect changes in an array of objects depended on how complex those objects were. Where else did we see a model of human behavior that was capacity-based? So this is good review. Think about attention, perceptual load theory, right? That is another sort of model that argues that attention is actually capacity limited. So this is sort of the same idea here. Short-term memory is capacity limited, right? It's like an engine, and there's only so much horsepower to go around. And so, it depends, our ability to use our attention to focus on things, our ability to use our short-term memory to remember things, right, depends on the task that we're doing, how hard the task is. Okay, we've come to the lecture review. Question 1, what are the 3 components of Atkinson and Shiffrin's memory model? So what are the 3 components of Atkinson and Shiffrin's memory model? Sensory memory, short-term memory, and long-term memory. Question 2, how much information does sensory memory hold? How much information does sensory memory hold? Sensory memory is a record of everything the senses are taking in, but this record disappears very quickly. So we could say that, sensory memory is really holding everything that our senses are recording at any one time, but this information disappears very fast. True or false? Short-term memory is limited to 4 items. Question 3, true or false? Short-term memory is limited to 4 items. False for a number of reasons. First, right, we can expand our short-term memory by chunking information together. Second, there's more evidence now that short-term memory is likely capacity limited, not item limited. So it depends on how complex those items are. If they're very simple things, maybe you can remember more than 4 items in short-term memory. If they're very complex, maybe you can only remember 2.